Hey everybody, it's Tuesday, January 26th, and as you can see here in the aim today, our goal for today's video is all about how we can refine our expression for gravitational potential energy, which eventually will lead us to be able to come up with an accurate physical description of a black hole. Ooh la la. So obviously, I want to, as quickly as possible, get to the good part. Obviously, the good part here being the part about black holes. And so let's just jump right into it. The way that we can sort of access this rather abstract concept is to engage in a fairly simple and straightforward thought experiment. And we can actually do this by just asking a bunch of fairly simple questions. What I want you to do here first is imagine a scenario. So I want you to imagine an object being launched from the surface of the Earth and is eventually just going to continue to travel away from the Earth. The object's gravitational potential energy is described by this equation, UG equals mg delta y. Of course, this being our fairly simple and straightforward equation for the gravitational potential energy of an object. The question we want to ask here is, well, this equation doesn't work well for the object when it gets far away from the Earth. Well, the question we want to ask is, why doesn't this equation work well for this object when it gets far away from the Earth? And this is like a really, really, really important point here. And so I want you to take a moment to really think about this very carefully. And I want you to take really a moment to seriously consider the issue at hand. And so in order to do that, I'd like you to go ahead and pause this video. So go ahead and pause this video here and think about the answer to this question. Why doesn't this equation work well? And if you think you've come up with the answer, hit play and we'll move on. So the answer to this question is actually rather simple and straightforward. And if you understand this, then the rest of this should be easier to access. According to our traditional equation for gravitational potential energy, the gravitational potential energy is based on three things. It's based on m, it's based on g, and it's based on delta y. M being the mass of the object, g, being the gravitational acceleration near the surface of the Earth, and delta y being the height. It should be pretty clear for everybody to understand. The mass of an object, as the object gets further away from the surface of the Earth, is not going to change, because mass is a constant no matter what. Height is also a pretty simple and straightforward measurement. It really just is how far away an object is from some reference line that we generally refer to the height being 0 at. G, on the other hand, while we usually think of it as a constant, 9.8 meters per second squared, is actually not a constant. If you remember, there's an equation for G, the gravitational acceleration. And it should make sense that the gravitational acceleration is going to change size with the distance because the gravitational force changes size with the distance. And so the idea here is that this equation, mg delta y, fails to account for the fact that g changes when you start to get considerably far from the Earth, because g is equal to gm over r squared. And so looking at that equation, we can see here that the gravitational acceleration is inversely proportional to r squared, just like the force of gravity is. And so if we were to plot that, g versus r, the graph would look like this. As you get farther away from the center of the Earth, the gravitational acceleration gets smaller. Now, it's important to emphasize one thing here, I think. G is a number that at a very small spread of distances is going to remain relatively constant. As we said, if you are comparing the gravitational acceleration at sea level to the gravitational acceleration at the top of Mount Everest, it changes by a very, very, very tiny amount, like less than 1%. However, if you are talking about a larger spread of distances, the object changing distances that are essentially larger than the height of Mount Everest, then what you're going to start to notice is that g is going to end up changing fairly significantly. And so the idea here is that when you're launching an object from the surface of the Earth, Yeah, once it reaches the height of Mount Everest, the G is not really going to change its size that much. But as you get farther and farther and farther away from the Earth, over that entire distance, G is going to be changing. And because G is going to be changing, we have to account for the fact that it is changing. And we're going to do that now. But first, I'd like you to take a minute to pause this video here and write this down, because this is the rationale for everything that we are going to do here for the rest of this video. So take a second to pause this here and write that down. And when you hit play, we'll move on. So the first thing I want to do here is I want to just basically incorporate what we just said about little g into our equation for the gravitational potential energy. Now, I don't think ultimately that this is too hard to understand, like to the point where you're going to have serious issues with it. But it is, this thing we are about to talk about is a little confusing. And so I want to take it step by step. And so the first step that we're going to take here is to very simply and straightforwardly just come up with a basic expression. And to come up with a basic expression shouldn't be that terrible. We have an equation for G. We have an equation for the gravitational potential energy. What we're going to do here first is just take our equation for G and plug it into our equation for gravitational potential energy. And so you could write this under the heading gravitational potential energy starting derivation. And so the first thing we're going to say here is that G is equal to big G m over r squared. And we also have, we are going to combine these equations, of course, that the gravitational potential energy, U with the subscript G, is equal to mg delta y. Now, the first thing we need to address here is that we have a little bit of a problem. That delta y is a measurement for gravitational potential energy that we usually make zero at the surface of the Earth. Whereas little g has a distance in it as well, r, which we usually make zero at the center of the Earth. But as we were saying, even though r is usually zero at the Earth's center, while delta y is usually zero at the Earth's surface, we always said so far that height is a measurement which is relative, meaning it doesn't really matter what you call the zero. You just have to measure all of your heights from that point. And so what we're going to do here is we are going to recognize that since we can play around with what we call zero in the gravitational potential energy equation, but not with the acceleration due to gravity equation, we're going to say that delta y now equals zero at the Earth's center. And so essentially what we're going to be saying here for this problem is that for this purposes of this equation, delta y is going to equal r. That delta y equals zero at the Earth's center. Now, this doesn't really matter, again, because height is relative. All we're really saying is that usually we call it zero at the Earth's surface, though not always, depending on the problem. We do it to make it convenient for us. Here, the definition of what's convenient for us is to make y equal zero at the Earth's center. And so essentially what we have here by making this substitution is we start with UG equals mg delta y, and we're going to make two changes to that equation. Obviously, mass is mass. G is G times the mass of the planet, and so I'll put a little subscript P on there for now, over r squared. And we said delta y here is going to be r. And so what we're left over with is UG equals G. Now I can write the mass of the planet and then just leave the mass with no subscript on it for the other mass, but we already have a system when we have an equation which has two masses in it. Think Newton's universal law of gravitation. We usually just write m1 and m2. And so that's what we're going to do here. And then, of course, because we have an r in the numerator and an r squared in the denominator, that r is going to cancel one of these r's, and so we're left over with g m1 m2 over r. This is our starting derivation. That now is an equation for the gravitational potential energy. Now, of course, we're not finished. And so let's put a little asterisk here and just mark that like this is unfinished because we have a little bit more thinking to do. And the little bit more thinking that we're going to do, at least here, I think should make sense based on things actually that we learned in honors physics and that you might have learned in chemistry. Take a second to pause this video here and write that down. And when you hit play, we'll move on to taking a more conceptual look at this equation. So now we have an interesting issue to deal with here. And the interesting issue is described by this note. It says here, as an object gets farther away from the Earth, the gravitational force gets smaller and smaller. And this should be clear to everybody because the force of gravity is inversely proportional to the distance between the objects squared, or the square of the distance between the objects. At an infinite distance from the Earth, the gravitational force becomes zero, which means the objects are basically unbound from the Earth. And so at this point, a point of an infinite distance away from the Earth, the gravitational potential energy would be zero. Now, this is a little confusing because essentially what we're saying is as you get farther and farther and farther away from the Earth, the gravitational potential energy increases, but then eventually you're going to get to some point away from the center of the Earth, and the gravitational potential energy is going to be zero, eventually. That is in contradiction to basically the way we think about all these other equations. Like think about kinetic energy. Kinetic energy is 1/2 mv squared. That tells you that as the speed gets larger, the kinetic energy is going to get larger. And as the speed continues to increase and increase and increase, at no point is the kinetic energy just going to become zero all of a sudden. It's always going to stay a number that's getting bigger and bigger and bigger. And so what we have now realized, if you think about this basic fact, is we have a little bit of a confusing notion on our hand. That even though gravitational potential energy increases as the objects get farther away from one another, eventually, once it increases and increases and increases, it increases to zero. And that should make you think of something pretty straightforward as to what we're going to have to do to that equation. But before we do that, take a second to pause this video here and write that down. And when you hit play, we'll talk about the last thing we're going to need to do to this equation. It should be clear to everybody that if you are lifting an object away from the surface of the Earth, you are doing positive work because you are increasing the gravitational potential energy of the object. But what we're saying is that if you're increasing the gravitational potential energy by putting in positive work, you're eventually increasing the energy to zero. And so now we have a very basic question to ask ourselves. How is it possible for you to increase a number and make it increase and increase and increase and increase until eventually it becomes zero? And there's only one possible way that that could happen. And that's if the energy starts negative. Now, what we've said so far is that energy can't be negative because it's a scalar and it doesn't have any direction. This is a slightly different point here. And it is unique to the type of energy that gravitational potential energy is. I'm going to go through and explain that. But first, I'd like you to take a second to pause this video here and write that down. And when you hit play, we'll talk about this in a little more detail. So if you remember in that previous slide, what I said here is that when you increase the gravitational potential energy so much to the point that the force of gravity ends up becoming zero because you're infinitely far away from the Earth, the object is no longer bound to the Earth. The force of gravity acts on all objects over infinite distances, right? Because the force of gravity is g m1 m2 over r squared. And so the only way that you can make the force of gravity between the Earth and any object zero is if the distance between those objects is infinity. Now, this is obviously a little confusing and abstract because infinity like in and of itself as a concept is kind of confusing. But as an object gets an infinite distance away from the Earth, the force of gravity gets smaller and smaller and smaller to the point where eventually, if it's a distance of infinity away, the force of gravity is zero. Now, you've actually already seen an example of this in chemistry because electrons are bound to the nucleus of an atom in exactly the same way that planets are bound to the sun or any object is gravitationally bound to any other bigger object in its vicinity. Now, the process of removing an electron from an atom, as I would imagine a lot of you might remember, is called ionization. And in order for an electron, or I guess you can say in order for the whole atom to become ionized, the electron really is just freed from the atom. In order for that to happen, you need to put energy into the atom in such a way that it increases the potential energy, in this case, the electrical potential energy between an electron and a proton, to the point where now the proton and the electron are no longer electrically bound anymore because the electron has gained so much energy that it's overcome that energy from the binding of the nucleus. So if you remembered in chemistry and in honors physics too, we looked at charts which look like this. And in these charts, what you should have noticed is that all of these energies for the energy levels in an atom were negative. And the reason they have to be negative is because we want to stick with the convention that if you put in work, that work is positive and that increases the energy. What we're saying, though, is for these kind of bound systems, increasing the energy eventually makes that potential energy increase to zero because now the objects are no longer bound to one another. And so it is a unique characteristic of binding energies, which really works for like gravitational attraction and electrical attraction. It is a unique case for binding energies that the energy needs to start out negative because if you add energy, it eventually makes it zero because the objects are no longer bound to one another. That's the idea. It certainly can be confusing, but it is an important point nonetheless. And so what we can do here to our equation is to just make the energy negative. And so the equation that we developed before is exactly correct. The only difference, or I shouldn't say it's exactly correct, it's almost exactly correct. The only difference between that and the true equation is that we need to put a negative sign on it. And so the final equation here for gravitational potential energy when the objects are far away from one another is we pop that negative sign on there. So we have negative G M1 M2 over R. And that's it. So here in this equation, G, I'm not going to write out all the words. It's Newton's universal gravitational constant. It's 6.67 times 10 to the negative 11 meters cubed per kilogram second squared. M1 is the mass of object 1. In most cases, we make that the Earth or the sun or whatever planet or star we're talking about in the problem. M2 is the mass of object 2, which is usually like a spaceship or some other object, perhaps an object in orbit. And of course, both of those are masses, so they're measured in kilograms. And a key thing to remember here is that R is the distance between the centers of the objects, as it was in the gravity equation. And so that's going to, of course, be measured in meters. And so that means the unit of the gravitational potential energy, of course, because it's an energy, is joules. Take a second to pause this video here and write that down. And when you hit play, we'll move on. Okay, so if you look in your AP Physics reference table, you should notice that this equation is printed in there on the bottom of the second page. And it says exactly what we said. The gravitational potential energy is gm1m2 over r, but negative. And again, the only reason why the energy equation is showing the energy as being negative is because of this. In all situations, positive work is defined as work done on a system, and that positive work, according to the work energy theorem, increases the energy. The change in energy there would be positive. Of course, now, though, we've got another issue that makes this equation a little confusing. And the issue we can lay out as follows. According to the equation UG equals mg delta y, that equation says when the height increases, the gravitational potential energy increases. We just derived an equation for gravitational potential energy. What does that equation say as the height of the object increases? Or what does it seem to say? Well, according to that equation seems to suggest that as r gets bigger, the gravitational potential energy gets smaller, right? The r is in the denominator. So when the r gets bigger, it makes the number there smaller. How do we reconcile those two things? How do we possibly recognize that these two equations seem to say different things as the height increases? Well, the key thing to remember is that this equation is much easier to interpret. And the reasonable interpretation that you would get is correct. Let's be clear. Gravitational potential energy absolutely increases as the objects get farther away from each other. Why? Well, think about it. If you lift an object up above the surface of the Earth and you let it go, gravity's going to accelerate it towards the surface of the Earth. And because gravity's going to accelerate it towards the surface of the Earth, it's going to get faster and faster and faster, meaning that gravitational potential energy turns into kinetic energy. And if you allow gravity to accelerate that object over a longer distance, then it is going to accelerate to a larger speed, which is going to make it faster, thus having a higher kinetic energy. And if it ends up with a higher kinetic energy, it's only possible if it started with a greater gravitational potential energy. So the gravitational potential energy definitely is bigger when the objects are farther away. Then the obvious question here is, well, then how the heck do we explain the differences between these two equations? The key answer to that question is there is no difference between these two equations. When r gets bigger, UG seems to get smaller, according to that second equation. But since it's actually a smaller negative number, that's actually bigger, thus saying the same thing as the simple form mg delta y. When you increase r, that number in magnitude is going to be a smaller number. But it's a smaller and smaller negative number. And since it's getting closer to zero, which eventually is closer to all the positive numbers, it's actually technically getting bigger. Now, usually, I have tried to condition you to stop thinking that -4 is smaller than +4. That's true for vectors. A velocity of -4 is not smaller than a velocity of +4. The only difference is the direction. But since this is not a vector, that kind of thinking does not apply. A smaller negative number is actually bigger than a larger negative number. Take a second to pause this video here and write that down. And when you hit play, we'll move on. Okay, so that's it for this new modified version of the gravitational potential energy equation. Now, notice by my saying, well, that's basically it for this equation now, we are not just going to do a basic plug-in example for this equation. And the reason why we're not going to do that is because you're never going to have to do that in this course. The main reason why we come up with this equation is so that we can come up with the next equation we're going to deal with. And that equation is for something known as the escape velocity or escape speed, usually referred to either way. And as you can see here from this definition, the escape velocity is defined as the speed or velocity needed to escape the Earth's gravitational field. Now, the reason why we get kind of lazy about distinguishing between speed or velocity here is because the direction is implied. if you're trying to escape the Earth's gravitational field, the direction is going to be away from the Earth. Now, depending on how you're looking at it, that can be obviously in any direction around the Earth, but at least it's away from the Earth is the basic point. And so it says here, theoretically, it's based on considering an object with an initial speed at a point in a gravitational field that will move out of the Earth's gravitational field to a distance infinitely far away and arrive there with a final velocity of 0. So the basic theoretical construct is the answer to the following question. If an object starting on the surface of the Earth were going to leave the surface of the Earth and continue in a straight line directly away from the Earth, what speed would it have to arrive at a distance infinitely far away from the Earth at the exact moment the Earth's force of gravity, which notice is always going to be acting opposite the direction this object is moving in, by the time the Earth's gravity fully slows it down to a stop? That's what the escape velocity is. Now, this is actually a very important number, despite the fact that objects are never going to be traveling to an infinite distance away from the Earth. This is a very important number for space travel because it determines the launch speed of various objects that are going to be sent into space. Take a second to pause this video here and write that down. And when you hit play, we'll talk about how we can come up with the equation. So the way we come up with the equation for escape speed or escape velocity is we do a basic conservation of energy analysis here. We have an object. Let's just say it's sitting on the surface of the Earth. So there's the center of the Earth. This thing is sitting on the surface of the Earth. And so it already is a distance r from the center of the Earth. And it's going to take off with some initial velocity, which we'll call v naught. That's essentially what we're solving for. We want to find out what that velocity is going to have to be in order for this object to get infinitely far away with a final velocity of 0. And so we can just set up a basic conservation of energy statement that looks a little something like this. The initial gravitational potential energy plus the initial kinetic energy equals the final gravitational potential energy plus the final kinetic energy. And here's the deal. Because we are saying the object is going to get to a distance which is infinitely far away, according to that new gravitational potential energy equation that we derived, when r is equal to infinity, effectively, the gravitational potential energy is equal to 0. And because the definition of the escape velocity is that that object is eventually going to reach a final speed of 0 when it arrives at that infinite distance, the final kinetic energy is 0. So what we're left over with is the initial gravitational potential plus the initial kinetic energy is going to be equal to 0. Now, that may seem weird on its face, that two things added together are going to equal 0 when those two things are energies, but it's very important to realize that the reason why that makes sense mathematically is because the initial gravitational potential energy statement that we are using here is negative. And so the expansion of that equation by plugging in the equations for those different types of energies ends up looking like this. And that means to solve this for the escape velocity, which notice I've taken off the v naught here, but nonetheless, it's that speed here in the equation. We can solve for that simply by starting by adding the equation to the other side. Notice all we really do when we do that is we just get rid of that negative sign. And so if you want to remember how to derive this, the basic idea is you set the kinetic energy equation equal to the absolute value of this new gravitational potential energy equation that we've come up with. And so to finish this off here, it doesn't require a whole lot of work. The mass of the object is going to cancel. And we've gone through this like 100 times, but just to drive the point home, the actual mass of the object doesn't matter when we're talking about gravity, right? Yes, it has more mass, so it'll have more inertia, but the fact that the object has more mass or more inertia means the force of gravity is going to be bigger, and so those two things have that sort of cancellation style effect. And what we end up with here when we solve this for v, is we move the 2 to the other side and we get 2g, because there's no longer two masses, we'll just write m, and then over r, and then a square root. And that's it. because this is called escape velocity, usually we put an ESC as a subscript on the V to stand for V escape. And that's it. That's our equation for the escape velocity. And so let's just go ahead and flesh that out on a separate slide. If you have not gotten a chance to write this down, though, I suggest you do. So take a second to pause this video here and write that down. And when you hit play, we'll go through this equation in a little more detail and define the terms. Okay, so this equation, as I mentioned, is an equation for the escape velocity. So we'll write V ESC, ESC for escape, is equal to root 2 gm over r, where m is the mass of the planet. I'll write planet/object trying to be escaped, or I'll just write being escaped. And that, of course, is measured in kilograms. And notice we should probably just say while we're on the subject, notice the escape velocity is directly proportional to the square root of the mass of the object being escaped. That should probably make sense, right? If a planet or object is more massive, you need to be going faster to escape its gravitational field. Well, the very fact that it's more massive means it'll be exerting a larger force of gravity on the object. And so that follows logically, I think. R here is the distance between the centers of the object. Now, this is true to start when you're considering this problem. Obviously, because the whole theoretical construct of this problem is that the object is moving away from the Earth, means that distance is always going to be increasing. But the point is, whenever the problem says calculate the escape velocity, it's going to say something like, calculate the velocity required for this object to escape the surface of the Earth, or if it's starting 100 meters away from the surface of the Earth or something. And so you'll be able to use that information to figure out what the distance from the center of the Earth is with that info. And of course, here we've already defined this a bunch of times, so I'm just going to write down big G here is 6.67 times 10 to the negative 11 meters cubed per kilogram second squared, where V escape clearly is the escape velocity / speed, and it should be no mystery to anybody here that that's going to be measured in units of meters per second. And so notice also, while we are on the subject, that the escape speed or escape velocity is inversely proportional to the square of the distance, meaning when that distance gets larger, the escape speed would be smaller. That, I think, should make sense. If this is the Earth and we're saying, comparing points A and points B, is it easier for the object to escape the Earth's gravitational pull starting at A or starting at B? It's easier starting at B because the distance is higher. And if the distance is higher here, that means that the object is not going to have to go as fast to escape the gravitational pull of the Earth, because the gravitational force acting on the object at point B, going back to the Earth, is already smaller than the gravitational force would be if the object was starting at point A. That's the idea. Take a second to pause this video here and write that down, and when you hit play, we'll move on. So as we already mentioned, I just want to sort of get this point down. We could ask simple questions here like, how can we describe the dependence of the escape velocity on the mass of the rocket? Notice the mass of the planet is in there, but not the mass of the rocket. The mass of the rocket, or object launching from the surface of this planet, or like the Earth, the mass of the rocket has no effect on the escape velocity required for the object to leave the Earth's gravitational field or the gravitational field of any other planet or star or whatever. The last question that we want to ask here, and then I'll have you pause this and write that down just because this is important, is for the same radius, if the object is the exact same distance away from the center of the Earth, how can we compare the magnitude of the escape velocity to the magnitude of the orbital velocity? Now, some of you might have noticed at this point that this equation looks kind of familiar, or at least I hope it looks kind of familiar. When we were talking about centripetal force and talking about how we can use the ideas of centripetal force to think about orbits, we said if you set the centripetal force equal to the force of gravity, you can come up with an equation for orbital velocity. That equation looks like this. V orbit equals square root of gm over r. The equation for the escape velocity is the square root of 2gm over r. And so what we're saying here is that since V orbit equals root gm over r, and V escape equals root 2gm over r, then the difference between these two values is a factor of root 2. Root 2, remember, is 1.4. And that's just like an interesting, quirky little relationship. If an object is in a stable orbit, whipping around the Earth in a regular, stable orbit, if they increase their speed by root 2, meaning they increase their speed by 1.4 times, they will be able to escape the gravitational field of the Earth. They would continue straight in a line tangent to the circle if they instantaneously were able to rev up their engines, and they would move in a straight line, escaping the gravitational field of the Earth eventually. Interesting little relationship. Take a second to pause this video here and write that down, and when you hit play, we'll move on. Okay, so let's go ahead and solve a problem. Before we do that, though, I just want to show you, because I think these old-timey devices look kind of weird. This item, device, whatever you want to call it, is called Luna 1. It is the first man-made object to attain escape velocity and be launched into a heliocentric orbit. Heliocentric means an orbit where the sun, helio, is at the center. And so essentially, because this object was orbiting the sun, it needed to get out of the Earth's gravitational field and get into the sun's gravitational field. And in order to do that, they had to launch it at a speed that was larger than the Earth's escape velocity. Interesting little historical tidbit. Of course, if you Google escape velocity or Google Luna 1, you'll be able to find out some more information about that. Now, let's go ahead and solve the problem. Let's find out what that escape speed is. This problem says determine the escape speed required for a 10,000 kilogram rocket to leave the Earth's gravitational field from the surface of the Earth. The fact that they're telling you it's from the surface of the Earth is a pretty big giveaway here as far as what you need to do. Because remember, we said the R in the equation for escape speed, or really any other gravity-related thing, is it's the distance from the center. If we're talking about the distance from the center of the Earth for an object that's on the Earth's surface, that's just going to be the radius of the Earth. And so if you look in your planetary data reference sheet that I first gave you, well, you should already know that G is 6.67 times 10 to the negative 11 meters cubed per kilogram second squared. That reference sheet will tell you that the mass of the Earth is 5.98 times 10 to the 24 kilograms. And it also tells you that the radius of the Earth, which is what we need here. Remember, R does not stand for radius. It stands for distance between the centers. But because we're on the surface of the Earth, the distance between the object and the center of the Earth is the Earth's radius. That's 6.38 times 10 to the 6 meters. And we're looking for the escape speed, or the escape velocity, which we will denote by writing V escape. So this is a pretty basic plugin. We don't need to go too nuts about this. The equation for the escape velocity is 2gm over r. So we'll put here V escape equals the square root of 2 times g, 6.67 times 10 to the negative 11 meters cubed per kilogram second squared. Multiply that by the mass of the Earth, 5.98 times 10 to the 24 kilograms. And we'll divide that by the distance between the centers, which happens to be the Earth's radius, which is 6.38 times 10 to the 6 meters. And when you do all that math, making very sure you take the square root, you end up getting 11,182 meters per second. And that's it. I think, as you'll find, this is a pretty easy calculation. And so effectively what this is saying is, in order for an object to be launched from the surface of the Earth and escape the Earth's gravitational field, it would need to be launched with the velocity of 11,182 182 meters per second, which is obviously pretty fast, but it's, as you could tell from the information I presented in the beginning, it is clearly attainable by man-made objects. And so that's basically it as far as these calculations are concerned. They're pretty straightforward, I think. And, you'll be given information like this. You don't need to derive the equation unless you're specifically asked to, and you plug it in, and that's that. Just in case you're wondering, that speed, 11,182 meters per second, is about 25,000 miles per hour. So pretty fast. And that's it for that calculation. Now, of course, we could ask a pretty basic follow-up question after this. Suppose instead of launching a 10,000 kilogram rocket, we launched a 20,000 kilogram rocket. How would the new escape velocity compare to the escape velocity for the 10,000 kilogram rocket, and why? The answer here is basic. There's no change. It's the same. Now, I just want to kind of clean this up a little bit, because before I said, remember, the mass doesn't matter because of that argument we've been making for a long time, that more mass means more inertia, but more mass also means a larger force of gravity. All of that is true. But we'd like to sort of extend that into a new energy context. And so the idea here is that, well, according to the gravitational potential energy equation, this object is going to have a different amount of gravitational potential energy based on its mass. And so because this object has a larger mass, its gravitational potential energy is going to be a more negative number, meaning we're going to need more kinetic energy to overcome that. The Earth is going to be pulling on this thing harder, so we would need to launch an object which would have more kinetic energy. But it's important to realize at that speed, 11,182 meters per second, the object would have more kinetic energy if it had more mass, if it was traveling at that same escape speed, because the kinetic energy is directly proportional to the mass of the object. So the key detail here is that the mass of the object does not matter. The only thing that matters is the mass of the object whose gravitational field you're trying to escape. And that's the idea. Now, of course, before we go, we have one big question to answer. And that big question to answer is, why are you false advertising in your videos and telling us this video is all about black holes? Because we haven't talked about a black hole once. Escape velocity is the concept that you need to understand in order to really understand, at least classically, what a black hole is. A black hole, note, is something that is so big and massive for its size. It has so much mass packed into such a tiny amount of space that when you calculate that escape velocity, 2gm over r, the mass is so big and the r is so small that this speed ends up being bigger than the speed of light. And so essentially what that calculation would say is you would need a speed to escape the gravitational pull of this object that is larger than the speed of light, which is the fastest anything in the universe can travel. And so since the speed required to leave this object is larger than even the speed that light can travel at, it's considered to be a black hole. Black holes always seem to us, when we're first hearing them described, like they're some mysterious thing that seems very hard to understand. Now, obviously, weird things happen in and around black holes because the force of gravity surrounding them is ridiculously large. But the point is, a black hole is basically just something that's really, really, really large in mass for its size. It doesn't necessarily need to be really, really, really small in its actual spatial size. The radius doesn't need to be particularly large or particularly small, but essentially, as you can see from this equation here, it's about the ratio of m to r once you consider that it has to be multiplied by 2g. And so whenever you see in a question they ask you anything about a black hole, like is it a black hole, or what would need to be the mass for this thing to be a black hole, you would keep in mind that the escape velocity for a black hole has to be greater than or equal to c, which is the symbol we give for the speed of light, which is 3.00 times 10 to the 8 meters per second. Take a second to pause this video here and write that down. And when you hit play, we'll take a look at one of these black hole questions. So I was flipping through a textbook to see if I could find a chart to show my students a couple of years ago. And I realized in one of the college physics textbooks I have, it says the radius that all objects would have to be in order to be a black hole, like the sun, Jupiter, the moon, the earth, and one of those objects was a Big Mac. And I thought that was kind of weird, so I figured, yeah, let's do a problem with that. I'd like you to do this one on your own. It says here a Big Mac has a mass of approximately 240 grams, which is 0.240 kilograms. It says, to what radius would a Big Mac need to be shrunken down to make it a black hole? This radius, just so you know, the radius an object would need to be in order to be a black hole is called the Schwarzschild radius. You can look it up if you want to, because there's a good Wikipedia with a nice chart that shows you the Schwarzschild radius for various objects like the Earth, the Sun, the Moon, whatever. Here, we're going to go ahead and calculate that for a Big Mac. So take a second to pause this video here and write this down. Set up your knowns and unknowns. To what radius would a Big Mac need to be shrunken down to make it a black hole? When you hit play, we'll go ahead and solve it. Okay, so essentially what we're doing here is we're going to be taking that escape velocity equation and we're going to be solving it for r. So the first thing we're going to do before we do any of this, right, is we're going to write down our list of knowns. So the mass of the Big Mac here is 0.240 kilograms. Of course, we know big G is 6.67 times 10 to the negative 11 meters cubed per kilogram second squared. We know here, of course, that we're going to need to make our escape velocity at least equal to the speed of light. And so for this, we're just going to make it equal to the speed of light in a vacuum. Obviously, if you make the speed bigger than that, you're going to get a different size radius. But this is just sort of like the minimum value for this thing to be a black hole. And then we're looking for r. So we start off with our escape speed or escape velocity equation. V escape equals root 2gm over r. And we're going to have to go ahead and solve this thing for r. So I don't want anybody to get confused by this when you're solving this. Don't make silly mistakes. You all know how to do algebra, though. The first thing you should probably do is just square both sides of the equation. So you're going to have that V escape squared equals 2gm over r. And now all you have to do to solve this for r is just switch the position of the V and the r. And so you end up with r equals 2gm over the square of the escape velocity. And so that gives us r equals 2 times g, 6.67 times 10 to the negative 11 meters cubed per kilogram second squared, times the mass, 0.240 kilograms, over the square of the escape velocity, which here we are using the speed of light in a vacuum. So that would be 3.00 times 10 to the 8 meters per second squared. And when you do that math, what you end up getting, frankly, is a ridiculous number. You get 3.557 times 10 to the negative 28 meters, or approximately 3.56 times 10 to the negative 28 meters. The smallest distance that human beings are currently able to measure is somewhere around 10 to the negative 15 meters. And that's very small. Like atoms are bigger than that. The whole point of this question, like obviously the fact that this one chart had a Big Mac in it, I thought was like amusing. But the real point we're trying to make here is black holes, in order for them to be black holes, are objects that contain such a large amount of mass in such a tiny amount of space. Because a Big Mac doesn't have a lot of mass, obviously, it's like a quarter of a kilogram. It would need to be shrunken down to such a ridiculously, unimaginably small amount of distance for it to be a black hole. For reference, because you use the mass of the Earth in another calculation, the mass of the Earth is 5.98 times 10 to the 24 kilograms. And obviously, you should at least have some sense that like the Earth is huge. In order for the Earth to be a black hole, you would need to shrink it down roughly to the size of a marble. It would need to be that huge amount of mass, 5.98 times 10 to the 24 kilograms, contained in such a small area that small area, or I should really say small volume, would be about the size of a marble, which is very tiny, obviously. And so black holes are really sort of unique, weird things because they, are unlike basically everything else that we've ever seen in the observable universe. That said, we know they do exist, and people were having ideas about these things, in the 1900s, that classically, in classical physics, using basic conservation of energy, we can come up with equations that rationalize the existence of them. And then, of course, now that we have advanced measuring techniques and fancy satellites and telescopes, we can confirm their existence. And with that, that's it for today. Have a good one, everyone.